So thanks a lot, everybody, for coming, even after reading the title. What I want to talk about today is inversion of short time Fourier transform magnitude measurements, effectively. So this is going to be, I hope, at least directly related to ptychographic imaging. It's sort of the motivation that I have for thinking about these things. So that's what you can expect. So this is going to be a special case of a phase retrieval problem. So just a little bit about general notation. We are going to have highly structured linear measurements of either a vector x, if we have a pre-discretized problem, or a function. I'm going to be mostly interested in trying to recover infinite dimensional functions. So we have highly structured linear measurements, but we're only allowed to measure the magnitude squared, I'll focus on in this case, of these linear measurements. So in particular, I'm going to talk a lot about recovering either x or f from measurements like this, but I just want to point out immediately that you can't recover them uniquely. You can see that if you have any unit magnitude constant that you multiply either of them by, and you can pull it through the linear measurements, and it'll be killed by the magnitude. So whenever I'm talking about recovering f, it's always going to be up to this ambiguity that's sort of inescapable. So hopefully that will not be too confusing. There are a lot of imaging applications that are related to these types of measurements, so that influence the structure in these linear measurements effectively, which sort of come to you from whatever imaging system you happen to be using. So X-ray crystallography is an example. The more engineering side, speech signal processing will be related to the measurements I'll talk about today. But maybe for this audience, the most interesting sort of related application is going to be ptychography. So let me burn this image into the back of your retina because it'll make it easier to understand why I'm thinking about the mess that you're about to see after this, I hope. Anyways, so here's my layman's view of ptychographic imaging. So we have a sample here, some object we want to image. We want to get a nice detailed image of this sample. So we're going to focus radiation onto a portion of the sample and observe a diffraction pattern that results from that portion of the sample. Okay, so the diffraction pattern is going to give us Fourier information, and our detector is going to sort of throw out the phase information effectively. So we'll get effectively magnitudes of Fourier transforms of the portion of the sample that we happen to be hitting at this moment. Okay, but we don't just want to image one piece of the sample. We want to image the whole thing. So we're going to take this probe or window or mask. I'm going to probably call it all of those things at some point. This pointer's a little weird. Put it over there. And we're gonna shift it. So we'll take shifts of our window or probe and overlap them. And we'll take many shifts of our entire sample, get these local diffraction patterns, and then try to take that mess of information and invert it in order to get a good recovered version of our whole sample. So that's sort of the game we're going to play here. So this is from a colleague's paper of mine at Michigan State where so I didn't generate the image. I have copyright permission to use it in my publication, so I have it in my slides. But this has something to do with I guess the electron density or whatever of the sample that's just color coded that way. I'm not exactly sure why. Now, all I want to get across here is that we have Fourier magnitudes coming from the diffraction pattern and shifts of that information that we get as we sort of move our probe around. So that's the main thing that I want to do to motivate these measurements. So simplifying to the one-dimensional case, what do our measurements look like? So we have F, which is going to be our sample or our big object we're trying to image. M is our mask or probe or window. we're shifting it around. So these L's are the shifts. And we collect Fourier information at each one of those shifts. And we get the magnitudes of those sort of Fourier transforms of that multiple of the shifted mask and the sample for different choices of k. Okay? So I'm going to analyze these measurements and hope to invert them. All right? They're going to be noisy. I'm going to have some noise added to every one of these measurements. I'll call it N, KL. It's not stochastic. It's going to include all kinds of discretization errors and round-off errors from the computation, everything. I'm going to throw everything in there, right? So a whole bunch of deterministic junk is going to be in there. So don't let, like, thinking about distributions on it be confusing. It's going to contain everything. Okay, so, yep, F. I'm going to conveniently assume that we have a finite sample because imaging an infinite one would be hard. So it's going to have support contained in minus pi to pi. Okay, that's a convenient support. You could rescale to make this happen. But effectively, that means I now can sort of consider recovering a periodic extension of F and work with trigonometric series instead of, it's Fourier transform. So I'll have integer frequencies going forward for that reason. And then there are a whole host of very interesting time frequency type of questions you can ask about this setup, which a lot of people have been thinking about. So Paulina Selenovic, who is going to talk, I think, tomorrow, has done a lot of work on this stuff. Rima Alafiari and Ingrid Dobishi have together and separately thought about some of these problems. I just noticed last week that Philip Groves has some new preprint about some of this stuff up. So there's been a lot of work in these areas, but still I would say many of these problems up here are largely open. So for the sake of understanding maybe what I'm mostly interested in, let's think about this. So we have our measurement operator, right? Maybe I'm going to have k times continuously differentiable functions that are compactly supported in minus pi to pi. Maybe I'm measuring those. And then you can start asking yourself, for what frequency sets and shift sets is this thing going to be invertible, and for which masks? Clearly the zero mask is a bad choice, so you can't use anything, right? So when do you even have something that's invertible? When you do have an invertible set of measurements, how smooth is it? I'm going to argue that we should care about how smooth it is. I mean, hopefully it's kind of obvious, but I like to, repeat obvious things multiple times, so I'll talk about that a little bit more. Can you, if you have, maybe you're designing a new detector, is there any guidance you can get by banging your head against this theoretical wall in order to come up with a probe design that's sort of optimal and gives you optimally smooth inverses? Maybe you can design a better probe or a set of frequencies and shifts to sort of come up with more robustly invertible sets of measurements. And sort of for theoretical issues, I'm also kind of interested in, generally you can only collect a finite number of measurements when you're imaging something. So if you really want to recover an infinite dimensional function, when you take a finite number of measurements, what can you say about the best way to come up with a finite dimensional approximation to this infinite dimensional function? So today I'm going to consider F to be fixed and talk about inversion and how it depends a little bit on M and things like that. I just want to point out, though, that you can also consider F to be fixed and learn your mask. It's entirely the same. If you do a change of variable here, you just shift in the opposite direction, so it doesn't matter. So sort of point that out. So my lame attempt to convince you that you should care about smoothness, if you like, machine learning is the following. So a lot of these problems in reality are blind sort of ptychography problems. You don't know what the mask is. And maybe you really want to prove something about a neural network or some other type of learning approach actually being able to solve a problem like that. So maybe, what could you do? Well, maybe you could consider your masks to be parameterized by some set of parameters, temperature in the lab, like stage, the setup of your stage, things like this. right? So you effectively have a different mask, maybe for every different parameter. And then if you know that for a certain class of masks that you get from your parameters, you have some amount of smoothness in your inverse for at least some class of functions f. And you can sort of classify how smooth things are by sort of saying that maybe these measurements have an inverse that has reasonable Lipschitz constants or Holder constants, something like that. Then there are, approximation theoretic results for neural networks that say you can learn a function that's smooth, but it depends on how bad or how large the Lipschitz and Holder constants are, so you sort of need to know something about that if you want to prove a theorem that's meaningful. So maybe you could consider some of this stuff to be a first step towards a type of blind deconvolution machine learning approach where you focus first on fixing one m and trying to see what the smoothness sort of looks like of your inverse of these measurements. And that's my sale to you if you like machine learning stuff. That's as machine learning as it's going to get. All right, so back to the easier problem then. So we have these continuous spectrogram measurements. A little bit more about the class of functions f you can think about. Again, this compact support, so we can talk about trigonometric polynomials would be important. I wanted to have at least a few continuous derivatives just to make analysis easier. Once you make this decision, this integral is going to collapse to be over this interval, so you can start approximating either m or f by a trigonometric polynomial. So one assumption we'll make about m is that it's sort of compactly supported in the Fourier side. So it has a finite number of integer coefficients and is a trigonometric polynomial. That'll be one sort of assumption we think about. Another one will be that it has compact support in space. So more like the actual picture that we showed before in space, where maybe it's more compactly supported than f, and you're sort of translating it over f and trying to learn something about f as a result. So we'll sort of think about both settings. Another sort of technical condition we want, if we want to be able to, at least as we take an infinite number of measurements, really reconstruct f, we're going to need it to have some Fourier coefficient decay of some kind. So we'll quantify that by saying that this quantity, which is effectively the maximum in a small kappa range of integer frequencies around any given n, should be monotonically decaying. So what does that mean? That means I have a fairly, in Fourier space, I want f hat to look something like this, where the distance between these peaks is always less than kappa, something like that. So you can change kappa as you need. It's a reasonable assumption, I think, to make about, especially for continuous functions, that this would be something you could hope for. All right.
Ask,
yes.
M having compact support makes sense. That seems like a reasonable assumption. Being a trigonometric polynomial, that one doesn't seem very likely.
Yeah, it's unfortunate because that's the one where you really have better theoretical results. Here's my hope that I can convince you. Suppose you have like some periodic lattice of atoms or a periodic grating that you shift around, and that could be your M. So it's entirely periodic. It's going to be compact in Fourier. So shift that around on top of your sample a few times, and you'll have something like that. Whether you can really do that in real life, I don't know.
Right, but if it's something like what you had in the first thing, where it's just a window.
Yeah, then that's the case where in space you have compact support. Yeah. There's some difference between or some similarity for either assumption in either domain that you can sort of pull out of the measurements. It's easier if when you have the Fourier assumption, but you can get things to work in either setting as long as there's some sort of compact support, and I'll try to tell you why that turns out to be the case. Good, yes. So, collaborators. let me point out my wonderful collaborators, in particular, this guy right here. Look at that face. He's right back there. Mike Perlmutter, he is on the job market. He knows things about theoretical proof techniques to handle imaging techniques like ptychography. In another side of his life, he knows about graphical neural networks and has another branch of research devoted to machine learning techniques like that. He seems like the perfect guy to put imaging together with machine learning. You can talk to him after the talk if you want, or you can invite him for an interview and talk to him even more. Anyways, so he's a postdoc at UCLA here. And up to other wonderful collaborators who worked with me on this, Aditya Viswanathan at the University of Michigan, Dearborn, and Nada Cecino at the TUM in Munich. Okay, so enough of that. So let's get to the invertibility of these measurements, what we want. So I'm going to construct an inverse for these things, for at least specific types of measurements, for specific choices of shifts and frequencies and masks, which, and the constructed inverse is going to be in the form of actually a fairly, a computationally efficient algorithm. So I'll talk more about that later. But it's going to be sort of theoretically a four-step approach. The algorithm sort of in these middle two steps. But I'll talk about recovering this function. It's going to be 4 steps. So we're first going to discretize our function so we can recover some, using a finite number of measurements, some finite dimensional object that will let us approximate f. After that, we're going to talk about using a sort of nice technique from the physics literature from about 30 years ago to solve a lifted linear system and get either xx star or the Fourier transform of x, Fourier transform of x star. We won't be able to get the entire thing, either of these matrices in their entirety, especially if we have an underdetermined set of measurements, which we generally will. But we're going to recover a portion of them. And depending on different assumptions we make about the masks, we'll get a different portion of them. And from that portion, we'll then have to try to solve for either x or the Fourier transform of x, which we can do by various angular synchronization techniques. I'll give you 2 examples of what those are, and you can look in the literature to find many more. And once you have these, you can use them because of this relationship to construct a trigonometric polynomial, which then we can prove is a good approximation to the original function f, assuming that f was smooth enough, et cetera, in the beginning. So I'll just, for lack of a better idea of what to do, just go through these 4 steps in order, because I can count in order. Yeah.
Quick question. So I thought, like, if you have the Wigner transformation, the Wigner function, that it is actually invertible up to a constant phase. So why would you need this angular synchronization?
Because we're going to get, we're going to use a modified form, and we won't have the entire thing. We're only going to get a portion of this. And then from a portion of it, we still want to recover up to a constant times the true object. Yeah. So, yeah, I'll talk about how that works in a second. But it is a nice technique. So I'll have the one slide summary of how the whole banana works, and then how we sort of modify things. Good. Other questions anyone has? I don't see anyone sleeping yet, so that's a good sign. All right, so here's the cartoon version of the theorem that we're gonna sort of do the hand wavy proof of here. We're gonna exactly reconstruct the finite dimensional signal if we're talking about finite dimensional phase retrieval, or in the limit as our number of measurements goes to infinity, a sufficiently nice function in the noiseless case. So we'll show effectively that for specific choices of shifts, frequencies, and masks, we'll have exact recovery if there's no noise. So yay, you can do phase retrieval in the non-existent setting of no noise. Okay, but we'll also consider measurement noise and sort of show that the inverse that we construct here is also smooth, or continuous at least, should say. It's going to be 1/2 Holder continuous. We can bound the constants by involving certain parameters which give us a clue of how we can maybe choose slightly better masks, things like that. I'll talk about that later. And the sort of algorithm we're going to use to construct this inverse turns out, like I said, to be actually an FFT time, so fast Fourier transform time type algorithm, depending on if you implement it in particular settings. So it's sort of a provably accurate direct solution technique that maybe you can use to initialize more traditional iterative recovery approaches. It's fast enough that it might be a nice, provably accurate initializer, and there are some initial work in that direction by some other folks at TUM that I'll talk about, or at least mention later. Okay, so walking through the 4 steps. So easy way to discretize, or sort of finitize, I should say, the spectrum of F and M. We'll just take trigonometric approximations by projecting onto the frequencies closest to the origin for a certain number of frequencies. So we'll do. So this will allow us to make things finite in the Fourier domain. And then there are sort of standard estimates that tell you that if you have k times continuously differentiable function f, that you'll have some nice decay in this approximation. So you can take this sort of approximation error and push it into the noise that I said are always on our measurements, and will contain things like this level of error. So that's step 1, fairly sort of standard thing. A little bit more, once you've made things finite in frequency space, you can take a set of samples in space from them, equally spaced samples in space. So the x, then our finite object, is going to become equally spaced sets of samples from that trigonometric polynomial approximation f, and now I have a concretely finite object that I can try to recover. Same thing for m. If it has, especially is itself a trigonometric polynomial, this will be completely accurate. If, however, it's really concentrated in space, it's not going to be concentrated in the Fourier domain. So in that case, you might instead just use W and take equally spaced samples of the object directly in space. So we also consider this sort of setup. Okay, and then you choose the degrees in a certain way so that your total number of measurements that you might take is going to be like D. So sort of technical details there. So that's that. And then you do this sort of standard thing. You do the approximation by trigonometric polynomials. You have bounded error, so you push it into the n that was sitting there. You can sample those in this equally spaced way, and there's no incurred additional error. Or you can do this subsampling in W. And so we're just going to pretend that our original continuous measurements were these instead, these discrete measurements, and then just push some extra error into the n's, and now solve a discrete problem. Okay? But what we're going to be solving for, just to keep in mind, when we recover x, assuming we can do that from these measurements, we're going to get samples from a trigonometric polynomial approximation to f, and that means we have an easy way of approximating the original continuous object. We can take its Fourier transform and use it to construct a trigonometric polynomial that should be close to f. So that's what'll happen there. Okay, so we've reduced it to the discrete problem. We are pretending that our measurements are this now for our particular x. So what are we going to do? Let's go ahead and rephrase what the measurements look like. I'm going to define mk to be like a kth mask, and it's just going to be a product of our window times this complex exponential at the kth frequency. So now I have a collection of inner product magnitude measurements, right, that are sort of given to me, each one by a frequency choice. So I can do that. So just redefining things. And now I use the lifting trick, and I see that I have this highly structured set of rank 1 matrices that I'm taking as inner products with xx star. But this is just a highly structured linear system that I need to solve, and if I can solve it, I get xx star, up to whatever noise level I have. As long as I can figure out something about the condition number of my linear system or whatever, it's just inverting a linear system, so it's trivial. All right, so that's sort of step 3 of the algorithmic part here. Okay, so we have linear measurements in XX star, and there's a sort of nice connection to Wigner deconvolution in the discrete case. So let me talk about what that is. So sort of this really nice trick that you can use to solve these types of measurements. So here are discrete measurements, and what we're going to do for each frequency and shift that we've acquired, I'm going to assume that I've acquired them all, right? So these are not underdetermined measurements. Let's suppose I really took d² measurements, all possible frequencies and shifts, which I don't want to do, but let's say I did, right? So I do that. I get a d by d matrix of measurements that have this form. So what this nice technique by Chapman, which I believe he published the year I graduated from high school, is the following. So you Fourier transform on both sides of your measurement matrix defined this way. This is, in this discrete setting, these are going to be discrete Fourier transform matrices that are d by d. And that will give you this result after some calculations that are slightly unpleasant. And so how will I interpret this? This object right here is an off diagonal of XX star, right? So here's x, here's the conjugate of x shifted by k. This is a shift operator, so it's an off diagonal of XX star. And the kth row of this guy is going to give me the Fourier transform of that off diagonal times stuff that comes from our window, which we've assumed we know, right? So this looks complicated, but we can compute it. We know what it is. So we compute it. We divide our Fourier transform measurements, which we also have, by the result of this. These are Hadamard products, by the way. So these are, that's what the open circle is. I'm taking component-wise products with these things. So I divide this out, take an inverse Fourier transform, and I learn an off diagonal of XX star. That's sort of my discrete interpretation of Chapman's result. So what happens if you don't want to take all possible shifts or don't want to take all possible frequencies? Because generally you don't. Every shift is an imaging process and takes time, and you generally want to take fewer shifts. So what happens then? So, well, if you subsample the frequencies, take equally spaced subsamples of frequencies and shifts, and right, so now we have k frequencies and L shifts. We can form a little k by L matrix of measurements in the exact same way we did before. We just have fewer rows and columns. And then we can Fourier transform each side with an appropriately sized discrete Fourier transform matrix and look at the entries and see what they look like. And we get this sort of complicated looking sum of objects that otherwise look very similar to what the original Wigner distribution deconvolution was giving us. Get sort of shifts of x with itself multiplied with itself. These are again off diagonals of XX star, sort of summed and mixed together with Fourier transforms of shifted versions of our window. Okay, so we have another linear system we need to solve. And there are ways to make it easier to see that this is solvable and then think about its conditioning. So one easier way to make this look a lot more reasonable is to do the following, which is one of the things we do in the paper. So let's say we take k equal to d so that this sum disappears. So we're going to assume our detector, our diffraction patterns, we can collect all the Fourier measurements we want. So let's say take k equal to d, and we just want to use fewer shifts. So if we use fewer shifts, only this inner sum is still left. To get rid of that inner sum over L, you can start thinking about conditions on your window. So suppose your window is compactly supported in space, for example, which is from the picture that I was trying to get burned into your retina, looked like something that happens when you have a large sample. Well, in that case, if you have compact support in space, it could be the case that as soon as you shift this window, it's shifted out of the original support of W, and so you get a small number of shifts that actually contribute anything here. Almost all of these terms just disappear, and so using support conditions, for example, on W, you can get some collapse here and sort of have a dramatic simplification that you can then solve practically the same way as you did before. So you can use tricks of that nature to make this system much easier to analyze. So we do things like that. Okay, so using tricks like that, we have now a smaller number of shifts that we get to take. We have this linear system. And it turns out that if you really look at what's going on, the off diagonals that we can actually reconstruct of XX star if we make these sort of support assumptions on the window sort of reduce what we can actually recover down to just a small number of the off diagonals from the main diagonal. So if you make one of those types of support assumptions, instead of recovering all of XX star, you instead recover some portion of it that's sort of a bunch of the diagonals periodic. So we get a bunch of zeros here. We can't see those entries of the matrix, but you can recover these things along the diagonal. So that's one example of the sort of reduction you can come up with. And now you have a portion of XX star, and you want to reconstruct X. Okay. So this is the simple solving of the linear system part of the, I think it was possibly step 2 or whatever of the talk that I wanted to discuss. All right, so here's an example of how, given something like that, a set of off diagonals of XX star, you can recover X pretty easily. So this is so let's suppose we've solved our linear system and gotten a portion of XX star. It's this. I have a few off diagonals, so there are zeros in there that I just couldn't see, but I've recovered the other entries by solving the linear system. Well, what can I do? So X has, it's just a vector of length 4 for the sake of making this easy to understand than actually fit on a slide. We notice that on the diagonal, which I can recover, I have the magnitude squared of each entry. So we can take the square root of the diagonal and get the magnitudes of X. Okay. And to get the phases of each entry, we can do the following, which is not quite as easy as taking the top eigenvector as you would do for XX star to get X, but almost as easy. So we'll normalize all the entries entry-wise. And when we do that, we have the phases left, which turn out to contain differences between the phase angle of the first entry in this case. So that's what phi 1 is, minus the phase angle of the second entry, right? So, and it's a symmetric Hermitian matrix. So we have conjugate down here, right? Second and third phase differences are going to be generated from this, etc. And it turns out, you can check if you don't believe me, that the true phases are an eigenvector of this. And not only that, but you can prove that it's the top eigenvector of this. So this is an example of sort of an easy eigenvector angular synchronization approach that you can use to recover the phases. And so you combine them with the magnitudes you pulled off the diagonal, and you get X back. Up to a global phase, because you can't actually just get the correct eigenvector, right? It'll be off by a phase. So there's your missing global phase. Okay, so that's an example of angular synchronization. Here's another even sort of easier way that you can do it if you have entries of XX star where you recover more scattered entries. You just sort of need just one entry, one column, one entry in every column of each row, and then you can do something like this. You can recover some other portion of XX star. So simplest possible angular synchronization technique, just to give you another example of how you could do it. You can only recover up to a global phase anyways, so let's just say the first entry of X is real. So I'll set the phase angle to be 0 because I can never know what it is anyways. So it's real. We're done. Then what do we do? Well, if we have the ijth entry of this matrix, I can normalize it. And I have the phase difference information here. And then I just have to have something that I can compare to 0. We'll then learn the phase of the other entry by using the phase difference information. Effectively, you can set up a telescoping sum that tells you, based on this phase difference information, what the phases of everything is by comparing everything to 0 to the first entry, which you've assumed is real. So you just figure everything out that way and come up with your phases. Yep.
So if you have a two-dimensional X, like an image, yes, then you would have two ways to go, or several ways to go to the same point. Like, I mean, the same problem is integrating a vector field, so to say.
You could probably average or something in that case. Yeah, it would be. This might be one of the reasons why. So this is sort of a heuristic observation, but the two-dimensional phase retrieval problem is sort of theoretically easier than the one-dimensional phase retrieval problem, and this is sort of the reason why. Maybe there are more ways to escape holes in your imaging technique in higher dimensions than there are in one dimension, and something like that. Yeah. I might retract that statement, but I think it's kind of true, at least in a highly sloppy and potentially incorrect way. All right, anyways. Okay, so there are multiple ways you can use to solve for the relative phases. So this is the third angular synchronization type step that I mentioned before. And there are more complicated things you can do, of course. All right, good. So now we've recovered X. We remember how we discretized. It should, if we take its discrete Fourier transform, it should give us good estimates of the Fourier coefficients for the original f. So we form a trigonometric polynomial called FE for estimate, I guess, and then go through gymnastics to prove that this is close to the original function and sort of bound the error. Okay, I have time left. All right. Okay, and the end result of all of this is our sort of pseudo theorem that we talked about before. So maybe I've convinced you even based on the discussion we just did that if you have no noise and you just have discrete measurements of this kind, you can exactly recover X, right? And that maybe you can exactly recover F if the number of measurements goes to infinity. You have to analyze all of the steps that I went through when there's noise to see what happens to the noise as you solve your lifted linear system and do the angular synchronization, normalizing the entries of the rank 1 matrix when there's noise added to things is problematic. You analyze all of this stuff and get some quantities I'll show you in a second that at least give you some idea about what makes noise tolerance better and what doesn't. Unfortunately, what we're going to see is that in the worst possible case, these measurements are not going to be super noise robust. So that'll be sort of a downside. On the other hand, experiments seem to indicate that the worst possible case almost never happens. I don't know what that means, but I'll try to make that a little bit more exact. So here's a theoretical statement that makes the continuity of the inverse a little bit clearer. And of course, right, I'm talking about Lipschitz or Holder constants here. It all depends on which norms you use to compare your solution. So this is for this sort of natural choice of errors that we're going to use. So what does this say? X is the original finite dimensional object. We invert these finite dimensional measurements and get XE. It's what comes out of our angular synchronization. We can only recover it up to a global phase, so we'll look for the best global phase, right? So this is our measure of error. You can bound that by this beautiful object on the right here. This bound is not tight, but I think it's it's tight enough to be instructive. So let me talk about why some of these things look this way. First, I'll point out this is the noise. This is the the L2 noise on all of the measurements you took. If there's no noise, you get exact recovery. You have 0 here, so that's good. If you do have noise, L is the number of shifts you use. More shifts, leads to better stability. So that seems to make sense. This is a case where we have maybe one of these periodic windows that we're shifting around. So there's sort of finite support in the Fourier domain of our window. The larger the support is, the more robust you are. So in some sense, having exactly restricted support makes the system easier to solve, but makes things less robust to noise. That you can actually quantify. That's sort of true. There are lower bounds that actually demonstrate that Mike and I have worked on in the past. You have these sort of quantities here, which you can remove these to some extent. But why is this type of thing here even, this minimum of the Fourier transform of x? It has to do with, intuitively at least, with the following simple type of situation. So suppose that the Fourier transform of x looks like this. So it's in magnitude. It does some stuff. It comes down and becomes 0 for a while. And then it does some other stuff and then becomes 0 for a while. Looks like this. So it has like islands, isolated islands of non-zero Fourier values. There's nothing stopping a function from having a Fourier transform that looks like this, right? The problem is if my window has compact support and I'm effectively shifting this window and hoping to get information relating this side to this side, I'm going to have trouble because the support of my window is less than this band of zeros. So there's no way I will ever get any phase information from this guy mixing with phase information from this guy. So this is related to something that appeared also in the analysis of one of Dobeshi's papers. And it turns out that you can still, if you work hard enough, recover the signal up to a global phase ambiguity on this half and another different global phase ambiguity on this half if you want. So there are things like that you can do. This non-vanishing thing here is just an easy way of saying that can't happen because you can never have 0 anywhere, much less a string of zeros. So that's why that's there. All right, a little bit more potentially useful, possibly. This mu1 tells you something about how good the window is in terms of helping to regulate smoothness of this function, as classified by having small constants here. So you can compute this Fourier transform for a given window, right? It's a discrete object in the discrete setting. And the larger that value is, the better the smoother your inverse is going to be. So this tells you something about good windows versus bad windows. So something you can check if you want. All right, I won't dwell on this. Here's compact support in space. You can get similarly ugly things. Here's approximating functions. So again, this is the sort of nicer setting where you have a trigonometric polynomial as your mask that you're shifting around. Your estimate E, D ends up being the total number of measurements you take. So if there's no noise and you let D go to infinity, you exactly recover F. That's nice. If you do have noise, then unfortunately, in the worst possible case, the more measurements you take, the worse your answer is going to get at some point. So there's a balance here. So like I said, the bad news is it appears as if the measurements are, and again, this is related to things that Rima and Ingrid have talked about. When you discretize and try to do function recovery, taking more and more measurements is not guaranteed to get you a better answer when you have noisy measurements. In fact, it can make things worse. And I think that's also an interesting and potentially true phenomena, at least for this set of frequencies and shifts that I've been analyzing. Are there better frequencies and shifts? Yes, there could be. Anyways, so some interesting phenomena, more theorems. For the sake of proving that there exist windows which are nice, you can construct them. Here's a sort of easy construction. I can take one of these trigonometric polynomial type masks and just dictate what its Fourier transform is using some quantities that are sufficiently, large in the first entry compared to the other entries, and then prove that that means that this mu1 parameter that says you're good is going to be non-zero. And if you want, you can play around more and sort of design things where you bound this below by certain quantities, so you can start messing around with window design to some extent. All right. You can sigh. Not only do I only have, you can be relieved, not only is there only 5 minutes left of this, whatever this is that's happening here, the theorems are over. Yeah, pictures, exactly. So these inverses are algorithmic. I said you can implement them quickly. So here are some sort of tests for actually recovering things from these STFT magnitude measurements. So what do we have here? We have compactly supported smooth functions, so C infinity functions, bump functions. And we're going to generate them randomly by taking shifts of a bump function and then taking random weights and just adding them together, right? So here's an example of a function created that way that's supported as it should be in minus pi to pi. So it's a compactly supported sample function. You can randomly generate this way by taking random combinations of bump functions. Okay, so we did a bunch of experiments on things like this, where in it's a complex valued function. Here's the real part. The imaginary part is another randomly generated one. You can randomly generate as many as you want and then run algorithms on them and see what happens. So whatever I say about numerics is on things that look like this, or certainly not realistic samples that I'm recovering, but they're actually functions that you can try to recover at least. Okay, so we add Gaussian noise to the measurements, and this proposed method is the solve a lifted linear system and do angular synchronization thing as I described it. That's what this blue line is. As your signal noise ratio increases, this is from the additive noise, you get better recovery. It works in practice. You can make it have better noise performance by doing some hacks and numerical refinements that I won't talk about, but you can increase its performance. And for the sake of comparison, this is HIO plus ER, which I'm told by ptychography specialists is still one of the standard go-to methods for recovering functions from measurements like this. So you do several iterations of hybrid input-output. It's an iterative technique interleaved with other iterations of error reduction, and you do several blocks of iterations of each in a row, and that's sort of the industry standard maybe now at this point, at least among certain folks. So you have similar noise performance to 600 iterations of this. So that's fine. Why should you care? Well, because the proposed method here is, this is a runtime plot. Here's the dimension, the number of measurements you take. Here's the execution time. The proposed method is way faster, orders of magnitude faster than 600 iterations of HIO plus ER. The refined version, which had similar noise performance, is also faster. So I'm not saying that this technique is better than HIO plus ER, because guess what? You can do more than 600 iterations if you want and get an improved answer. But people have looked at this sort of variations of this proposed method as a way of initializing an iterative technique like HIO plus ER, right? These iterative methods are highly sensitive to where you start. You would want to start close to the global optimizer if you can. This is a provably accurate way of getting you close to the global optimizer, and then you can improve it by running your favorite iterative technique of choice. So I recently had a fun time, honestly, reading Ole Melnick's thesis. He's a graduate student at TUM, working with Felix Kramer and Frank Filber. And he's done some really nice work using variations of this proposed approach to initialize standard iterative techniques on, really realistic ptychographic imaging data. So,
do you know how many iterations you get it down to versus 600 if you initialize with this approach?
So this approach, the way I look at it is this approach is worth 600 iterations of HIO plus ER, except you can get there faster than doing 600 iterations. And HIO plus ER is also highly dependent on how you initialize the thing. So sometimes it'll just, an iterative technique will just get stuck somewhere. But if you initialize this way, it'll actually end up going to a better place. So it seems to help. All right, and I better stop. All right. Thanks a lot. I'll cut it off here.